Hello everyone, I'm Amir, and today with my friends Manish, Sitaram, and Rupesh, we're going to explain to you the project 4 of Introduction to Computer Communication Networks. In this project, we're evaluating the performance of IEEE 802.11 standard based on some parameters that we've defined for it, like the minimum and maximum size of contention window and the access method that we use for it. So first,
I'm going to explain about contention window, differences between 802.11 and 802.3, and why we are using CSMA CA or CSMA CD.
I'm going to explain the coding part of this project and what are the modules used and how it is done. It's going to be explained by me.
Hi everyone, I will explain the results part. This project has many combination of outputs, the use of RTS, CTS, and how the use of RTS, CTS is going to affect our simulation outputs. And as we will see, that the use of RTS, CTS just reverses the outputs of the basic rates.
in IEEE 802.11, the contention window size is between a minimum and a maximum amount, both of which can be fine-tuned based on our network and our traffic. This standard also has two access methods, which are BASIC and RTS-CTS. So the aim of this project is to evaluate the performance of the network based on each of these parameters, and also see how each of these parameters affects the network performance at the end. So to give you an overview of the number of variations that were studied in this experiment, we can see that contention window has a minimum amount of 32, 64, or 128 bytes, and the maximum of contention window can either be 256, 512, or 1024. Two access methods of BASIC and RTS-CTS were analyzed, and the packet size was assumed to be either a fixed amount or a variable amount, both of which will be discussed in details in the next slide. So 3 times 3 times 2 times 2 total variations were studied, which makes it 36 in total. Now, in IEEE 802.11, the frame size cannot be any number. It has some limitations. In this standard, the frame size is assumed to be between 0 to 2312 bytes. But since we're using CSMA-CA, the packet size can't be less than 60 bytes. So, in this project, for fixed packet size, we assumed the size to be 1024 bytes. And for variable packet size, we assumed it's a random number between 60 and 2312 bytes. Now, the performance of the network can be better analyzed through several parameters. The most important one of the most important one of them is throughput, which basically means the number of successful transmissions that we have and the total amount of data that we could send successfully. Now, throughput is very important in a network, but is not the only thing that matters. Another thing that we should analyze is the efficiency of the network. So the higher the efficiency of the network, the less the amount of failed transmissions, which results in more efficient power usage and other things like that. Also, busy time is important for us too, uh, because we need to see out of the total interval that the experiment was running, how much of it was used effectively to transmit data and how much of it was basically wasted in this process.
Before moving to the coding part, let's briefly discuss about contention window concept in 802.11. There are three basic techniques or steps used by CSMA CD to avoid collisions. They are interframe spacing, contention window, and acknowledgements. Interframe spacing is nothing but the time interval in which frames cannot be transmitted by stations within a basic service set. Acknowledgement ensures or guarantees that the receiver received the data. Contention window. What is contention window? It defines a period of time in which network operates in contention mode. In contention mode, time is divided into slots. A station which is ready to transmit the data chooses a number of slots randomly. So, these slots are defined as the station's wait time. So now, how the slots are chosen by the station? It uses the binary exponential backoff strategy to change the number of slots in the window. What is binary exponential backoff? It is set of one slot the first time and then doubles each time. So let's consider the example. The station chooses a random number of slots between 0 to 1. If the first collision is detected, it waits for 0 or 1 slot times. After the second collision occurs, the station waits for anywhere between 0 to 3 slot times. And if the third collision occurs, it waits between 0 to 7 slot times. So from the example, as the number of collision increases, the number just changes exponentially. In the contention window, the station has to sense the channel whether it is idle or not. If the channel is sensed as busy, the station just stops the timer and wait till the channel is sensed as idle. CSMA-CA over CSMA-CD. As we all know, CSMA-CD is employed in wired networks, such as Ethernet. It operates by detecting the collision. The sender stops transmitting the data once the collision is detected. But in CSMA-CA, the collision is avoided. It does not deal with the recovery after the collision. It just checks whether the channel is idle or busy. If the channel is busy, station waits until the channel remains idle. This results in reducing the probability of collisions and increases the efficiency of the channel.
Let us see the coding part in this project. Before going into the code, the coding in NS3 involves various factors like defining the nodes and installing them, the type of channel used and setting the channel attributes, the protocols used, etc. and etc. Let us jump into the code. Initially, we are defining a function called experiment. In this experiment, we are just changing the values called CWMin and CWmax. What are these? CWMin is the contention window minimum period and CWmax is the contention window the maximum period. These are user reprogrammable, like we can change the values at what are the values we need and we can run the code. The next part of the code is the mobility. Mobility is useful for just moving the nodes to the random position, and the function used here is course change. In this function, using this function, the mobility of nodes is possible. In this experiment, we just add this line in order to enable or disable RTS CTS in it. And the next is we are just defining the variables. Like here, we just add up how many nodes we need, like CSMA, Wi-Fi, etc. etc. And this CMD is useful to set the default value of an attribute from command line. Command line is a class file here. In this class file, use an object called CMD. Due to the limitations in the bounded area, we just add up an condition in the code. Like if the number of nodes of the Wi-Fi is greater than 18, we just print a statement that the number of Wi-Fi nodes exceeds
the limit, and therefore the program gets exited because of the error we have. The next condition, what is if verbose is true? Verbose is something that allows to picturize what is happening in the logs. Logs are nothing but which are used for logging of the systems. They are just used for logging of information. The next part is used to create the nodes. The nodes are created using a class called node container. This node container are useful to create many number of nodes, like different types of nodes like point to point or CSMA, etc., etc. In this project we are just creating point to point nodes. In this point to point nodes, the number of point to point nodes we needed are 2. So after creating the nodes, we have to use the helper, like what is the communication channel that you want to use to communicate between these two nodes, and that is being done using this class called point to point helper. And this point to point helper contains a class file called point to point, and this point to point is the channel that is required for the communication between these nodes. And the next part is to set the channel attributes. And using this command, we are just setting the channel attributes like data rate, delay, etc. and etc. Similar to that case, we are just creating the CSMA nodes as well. But before creating the nodes, we just need to install devices on it. Like we have created the nodes, we just set the channel attributes and the channel used in it, and what we have to do is to just install the nodes. Like without installing them, it's waste of doing the project. Like that installation can be done using a class called netDeviceContainer. In this netDeviceContainer, we have a object called point to point devices. So this using this point to point devices, we can install the point to point attributes to these nodes, and this can be done using this command. Similarly, we just create the CSMA channel and just set the channel attributes, and just we install the CSMA nodes onto the network. The next part is creating the Wi-Fi nodes, and it is done using the node container class as well, and it creates the Wi-Fi nodes, and the number of Wi-Fi nodes are declared previously in the defining variables section. So after creating the nodes, we just need to create the channel that are useful for transferring the data, the mode where the data has to be transferred or received. The path, the communication link is called channel. That channel can be created using YANS Wi-Fi channel helper, and using that we have created the channel between the Wi-Fi nodes. So with the Wi-Fi channel helper, we are going to set the attributes in it, and this is done in these 3 lines of code. After installing the channel, and we have to install the nodes, so that can be helpful using this class called netDeviceContainer. Using this class, we are going to install the Wi-Fi nodes. And next is the position allocator for mobility models. Like the mobility model is helpful, it can be done using the class called mobility helper. And this in mobility helper, using the mobility object, we just position the node, like using the set position allocator. Using defining this thing can be done using the code. And the mobility model attributes are defined using these lines of code. Like we have to deploy the system in a squared area, so that's the reason we defined the values as -100, 100, -100, 100. These are user reconfigurable, like we can change it to any number of any values that we decide to do. After installing the channel, after creating the nodes, defining them, and just creating the channel and setting the attributes of the channel, the next part is to ask nodes to follow certain rules while transmitting and receiving data. That can be done using a class file called Internet Stack Helper, and which uses an object called stack. This stack object is used to install certain rules on the nodes such that proper transmission takes place. After setting After setting the rules, we need to assign the addresses. So that can be done using this IPv4 address helper, and this class file is used to assign addresses. So the base address set for point-to-point interfaces is 10.1.1.0, and the 255.255.255 is the subnet mask of this point-to-point network. And for the CSMA, the address set base is defined here and the subnet mask is defined here. After assigning the addresses, we just go to this part of code, that is the application part. In this application, what the necessary things required are how we want a program to execute, like what type of application is needed. That can be done using this line of code. Here we are taking an echo server application, and that can be taken using the class called UDP echo server helper, and this 9 represents the port number of it. After that, we just install this application over our nodes, and we define the server start time and server stop time. Similar to that of server application, we create a client application as well. The client application taken in this project is Echo Client application, and that application can be taken using a class called UDP Echo Client Helper. And after defining the application, we just set the attributes like maximum packets, interval, and packet size, etc. etc. These parameters are user reprogrammable, like they can change the values and can run the code as many times as possible and check for the results. Similar to that kind of server, we just define the client start and client stop times using these commands. The next part is the flow monitor. Flow monitor is a useful module in the part of NS3, like it calculates many values like that are useful for the user in order to estimate the performance of the network. We can calculate throughput, we can calculate transmission efficiency, all that stuff can be calculated using this flow monitor. And we need to run the code, so that can be done using simulator run command. In order to display the results, we just use all the stuff, like we just formulate the thing in the flow monitor, and the flow monitor displays the result in the form of an XML file. We have to download the file, and we can view that file using Excel or any other software. This is the main part of the code, right? We are going to print two statements, that is experiment with RTS-CTS disabled and experiment with RTS-CTS enabled. So before printing the next statement, we add up a line called experiment false. That goes to the main function. If the experiment is false, it comes under the basic running of the code, like without RTS and CTS. If we need RTS and CTS, we just add up this line and make the experiment true.
Let's now analyze the results. So as we have already discussed in the presentation that we have 36 different combinations, and the combination about condition with the minimum size and maximum size, where the minimum size goes from 32 bytes to 64 bytes to 128 bytes, and the maximum window size is 256 bytes, 512 bytes, and 1024 bytes. And we have the two different access methods, that is basic access method and the RTCTS methods. And also we have different packet sizes. We have a fixed packet size and a variable packet sizes. So I will go into these different combination and their effects one by one. So let's start. The first combination or the result is about condition window size versus ratio of buffer load and the carried load. So when we checked for this basic access method, we found that when the condition window size is small, we have better offer load versus carried load ratio. And the best one which we obtained was about 128 to 512 and 128 to 256 condition window size. And for the RTS and CTS case, it was totally a different scenario. When we have a larger window size, we got a better ratio of overload versus carried load. And this is quite logical also because RTS and CTS avoids collision in a much better way. So our next analysis was done between the transmission probability and the throughput. Unfortunately, for both the access methods, we did not establish any constant type, but generally throughput decreased when transmission probability increased, and it holds good for all the packet sizes. The next one was between analysis between the number of nodes and the throughput. Now, this analysis gave a very interesting results. The first case when we kept our packet size small, our throughput kept on increasing the number of nodes. And when we have a larger packet size, throughput first increased and then decreased on increasing the number of nodes. So on when we checked about the CSMA and its about principle, so this result holds very good. Because as per CSMA principle, as the number of packet size increases or the number of nodes increases, we get more and more efficient network. The next one was about number of nodes and idle time, and this result was quite apparent and quite straightforward. That when the number of nodes increased, the idle time also decreased. It's quite logical. The next result was between backup stage and the throughput. So as per the condition window minimum size and the maximum size, we had 5 backup stages 1, 2, 3, 4, and 5. And when checked for the basic rate, throughput was best for the backup stage 1 and backup stage 5 because in the both the stages we have a maximum difference between the condition minimum size and the maximum condition window size. And for the RTCT's case, the throughput kept on decreasing on increasing the backup stage because idle time increased as the backup stage increased. And for the last case, we have about packet size versus throughput analysis. And as per the CSMA and as per our simulation also, as the packet size increased, our throughput also increased. And it also makes the network more efficient when we have a more and more packet size nearer to the MTU. And one other interesting result was about the condition window. If we have a larger size of condition window, we have a better throughput. So friends, that all is about analysis of the results.
Thank you everyone for your attention. I also have to thank the Department of Electrical and Computer Engineering, Purdue School of Engineering and Technology, IUPUI. Also, I have to have a special thanks to Dr. Damsu Kim for his mentoring and his help throughout this project. If you have any questions, don't hesitate to ask us. And again, thank you for your attention.